Hello, sixth graders, and welcome to my YouTube channel. Today we're going to do some more work with these operations, specifically assignments on these operations. One of the assignments that you had from the previous day's work, of course, you were given one of these little machines, and this idea of these input machines. On this example, right here, for instance, we can look at this and say, okay, I need two numbers that when I subtract in mod 7, the answer is 1. Well, the good news is that's relatively easy to do because, as I can, you may say, oh yeah, 5 minus 4, that would be 1. But understand, on this kind of open sentence like this, when you've got those two spots, there's actually going to wind up being 7 pairs of numbers, mod 7. There's going to be 7 pairs of numbers at work. 1 minus 0, sure. But don't forget the 0 minus 6, because when you have 0 minus 6, you really, in fact, have 7 minus 6. So, on part A of this particular exercise, you're looking for two numbers that when you subtract them in mod 7, it makes 4. So again, people seem to have no problem finding 6 comma 2 and 5 comma 1 and 4 comma 0, but those aren't the only ones, because again, if I add 7 to 3, I now have 10 minus 6, but that's not the ordered pair I put. I have to put 3 comma 6, and these pairs, you're putting them in parentheses as you're typing them in. Again, I have 7 pairs of numbers for this. There should be 7 pairs for this, and B is relatively simple. I'll leave that one for you if you haven't tried it yet. Now, as you continue to work in operational systems through page 52, exercise 55, that's what I'm going to assign for today, use the following pages to guide you in your work and what needs to be in your notebook. So, in the notebook, of course, I'd like you to highlight the minimum operation here. When you learn that something is an operation on a set, what does that mean? What it means is that no matter what two values I use, from the set, the answer on the operation has to be on the set. So the lowest number function here, as we see, you see a little arrow pointing down, 6 and 4, it leads to a 4, which is in fact going to be a whole number. Because right here, my minimum operation, I'm defining that as, for all x's and y's in the set of whole numbers, that's going to, that's going to be an answer on a whole number. It has to be. So that's what we mean when we talk about an operation on a set. Incidentally, so, to give you an example, you say, well, what's something that's not on a set? Well, how about whole number subtraction? That would be an example of an operational system that is not actually an operation on the set. So therefore, it's not a valid operational system. The reason is because if I take 2 minus 5, we agree that 2 and 5 are both whole numbers. And many of you already know about integers. Negative 3 is not a whole number. Your whole numbers, so that's going to be a problem. Your whole numbers are just going to be those numbers, 0, 1, 2, 3, 4, and so forth, right? That's the set of whole numbers. The set of natural numbers, by the way, is almost exactly the same. It's just 1, 2, 3, 4, and so on like that. Okay? So, on exercise 51, I want to give you a little bit of help here. They give you this table, and students get very, very confused by this, because the idea here is that you have these operation tables, and it's only on 2 elements. It's on Z sub 2, which is just 0 and 1. So when I have some operation table, such as you see right here, there's only a certain number of operation tables possible. This is where it's confusing, because some people will look at this and think, well, maybe I'm supposed to try to figure out is this addition? Is it multiplication? Is it some combination? No, you don't even have to worry about that, kids. This is why I said people get confused on this. Simply just look at this. That is, whenever I line up these tables, I mean, if I said multiplication over here, this table now makes sense, doesn't it? Okay. Now, but again, I didn't have to do that. What I'm trying to tell you is that you're completing, there's a whole bunch of squares on exercise 51. Go look at it right now. How many different operation tables can you complete? Even though we may not know what the operations are. So I could have all zeros like that. I could have zeros with a 1 in the bottom right corner. I could have zeros with a 1 in the left corner. How about zeros with a 1 in the top left corner? What if I did something like that? What if I have all 1s and a 0 there? Now are you understanding how you're filling in all these? So the examples I just gave, you can start filling those in. Again, check out what I highlighted here. I said there are fewer than 18 such operations. They give you 18 boxes and 3 of them are filled in to try to give you an example of what you're supposed to do. You're not going to fill them all in. Your goal is to figure out how many you should fill in and make sure you don't have any of them matching. Again, I don't want to give away how many you're going to do, but it's going to be fewer than 18. Good luck with that. Give it a shot. Now let's move on to machine diagrams here. As you can see with these machine diagrams, we can actually start chaining them together. Put at least one of these examples in your notes, by the way, because there's eventually you get a test question and people say, wait, what am I supposed to do with these? The idea of the machines is that you kind of work your way down, so go highest to lowest. So the way this one's arranged right here, this tells us we're going to add 2 plus 1, which we know is going to be 3, and now 6 times 3 is 18. Yeah, it makes sense. Over here, we're doing 6 times 2 on that one. And then on this branch here, we're doing 6 greater number function with 1. So that means I'm choosing the larger of the 2. Yeah, it's a 6. And 12 plus 6, of course, we can see that that is going to be 18, as you can see. So as you're looking at these diagrams, again, you can read, once you get the idea of what's going on, you could actually just say, oh, this is a mathematical expression, this machine diagram, this, made up machine diagram, can be thought of as, nice sentence. Whenever you have something above, such as this one, think of it as saying, hey, I have to do this operation first. Now, whenever we want to do an operation first, we can wrap it in the parentheses. That's why this expression is going to require the parentheses, because if I don't put parentheses, it's going to read it as 6 times 2 plus 1, which is not 18. See the problem there? That's why it requires parentheses. We must say that we mean to add the 2 plus 1 first. So notice on this one here, what do we have? We've got 2 plus 1. There it is. When I add those first, it gets me to 3, and that's going to result in 18. If I change where the parentheses are, that's going to yield a different set of parentheses. So as I showed up here, yes, that's why we need to use the parentheses. On some of these operations, you're going to see the order does not matter, and thus we could say these two machine diagrams are equal to each other. So that's a 5, that's a 5. Can you think of another operation where the order doesn't matter? Did you say multiplication? I hope so. That's a good one. This is a special property that's very, very important at multiple levels of math, and we're going to call that the commutative property, or commutative law, as they say in the book. Commutative law, this is something that should be in your notes, because this is something you're asked to know and know it cold. Commutative law means that I can change the order and the operation result is still the same. The assignment is still the same, whether it's x plus y or y plus x. Now, here's another law involving addition and multiplication machines. Notice if you have x plus y right up here times the z, yeah, I can write, based on what I just said, I know that x plus y is supposed to be done first. And I'm now saying that this is equivalent to, the x times z plus y times z. This is a little something called the distributive property. Again, put this in your notes. If I replace x, y, and z, by the way, sometimes this is confusing. I'm sure you're looking at this saying, oh, well, all these letters. And don't get cowed by the letters, folks. Just make up numbers, whatever you want. Let's just say x is 2, y is 3, and z is 4. And then now let's see, do those work here? If I put 2, 3, and 4 in place of these. So there, I said y. There we go. 3 times 4. And this is going to make a 5, because 2 plus 3 is 5, and now I multiply by 4, and that's 20. Over here, I have 2 times 4 makes an 8, and 3 times 4 makes it 12. And pretty clearly that I can see 20 is going to be the result on either side. That is the distributive property. Again, please know that one. Very important in 7th grade. So as you go to do page 52, on this one, you're trying, it says, and right here you have the directions. Please read the directions. Check inside the box for the selection that says these machine diagrams are equal, and you'll see a menu pop up that lets you, if you're saying, oh, look, these are equal, your menu's going to pop up and you're going to select the operation symbols, multiplication, up arrow, down arrow, since they're not on your keyboard. And that's how you enter those symbols. If you're going to use plus in your machine, that's a symbol you can use on your keyboard. But you write both sides of the equation, include all necessary parentheses. So if they're not equivalent, then you're going to give some values for x, y, and z. So again, if you're saying these are equal, if you hit this, it's going to pop up and say, okay, so what's the statement? And here's the directions for that one. So if you're saying they're not equal, that means I can put values of x, y, and z in here, and I can just make up numbers again. Let's say x is 2, y is 3. I'll go z is 5 since I said 4 last time. All right, so when you're trying that, just try this out on paper. Just sketch this out on paper and see if it works. Let's see, greatest number between 2 and 3 is got to be a 3. Okay, greatest number between 2 and 5 is a 5, and the lowest number between them is a 3. Alrighty, so then over here I've got what do I have, 2, and then I've got a greater number function like so. And greatest number function between 3 and 5 is a 5. Lower number function here between these two is a 2. Ooh, I can see that these are not equal. Maybe I should erase this because I just gave you an answer for this exercise, didn't I? I just answered A for you. But, okay, so don't do 2, 3, and 5. All right, nothing's really stopping you. You can enter whatever numbers you like on the grader. When you're using the EMF, these types of exercises, it actually checks the math and makes sure your math checks out. It's kind of cool. Sorry for the long lesson today, but I thought it was important I get all those things in. I'll have office hours later today. If you want to check in with me at 2:30, we can go over what you need to go over at that time. In the meantime, go ahead and do exercises 50 through 55. It's pages 46 through 52. Thank you for watching today's lesson. Subscribe to my YouTube channel and smash that like button, and I will see you later.